All right, so let's start. Last lecture we were looking at a BJT amplifier, and we had said that if we take a transistor and simply attach a source and attach a load, is not going to amplify. What you have to do is take the transistor, up, bias it in the forward active mode, somewhere in this flat region here, and then if you apply, after biasing, if you apply your source and you connect a load, you may get amplification. All right, so the purpose of biasing then is to attach some circuit here, some circuit here, some circuit here, to push the transistor into the forward active mode. All right, and so not only that, remember the amplifier amplifies the signal which is connected to it. And the whole purpose of amplification is to obtain power which is delivered to the load. And so the supply and the biasing circuit and all that you see here is not only there to push the amplifier into the forward active mode, but also to supply the power. The power which is delivered to the load comes from the supply here. This signal only modulates the power. Okay. All right. So, and we said that while biasing, because we'll see that all the amplifier's characteristics depend on the transistor bias current and bias voltage, we have to make the bias stable. And now, when we say stable, what is it? We have to ask ourselves, what is it that is causing the deviation in the bias point? One of them is that with change in temperature, the base emitter voltage deviates from its normal value. Approximate deviation is 2 millivolt per degree Celsius. Even more important than the deviation of the base voltage with temperature is that the beta of a transistor can vary considerably. It can vary even from, if the nominal value is 200, it can vary from 100 to 300, maybe as much as that. And therefore, what we want is that our circuit should be, when we bias it, it should not be very sensitive to beta. If it's very sensitive to beta, then I want my transistor to be biased at, let's say, 1 milliampere, and you get 1 milliampere at a beta of, let's say, 100. But when beta goes to 200, you get 2 milliamperes. Or when beta goes to 50, you get half a milliampere. If the current would change in that manner with beta, then the whole biasing point is affected, and the whole transistor performances, whole amplifier performance is also affected here. So if you recall, last lecture's discussion was the traditional discussion of amplifier begins with a circuit like this, where we use a source, we use a battery with a resistor RB, and along with the resistor here and a source here, we bias it in the forward active mode, and then we attach a signal here, which is then we want it to be amplified and appear over here. And we saw that for bias stability in the sense that, remember, I talked about only beta and temperature, but then there are many other things that vary. The supply voltages may not be 5 volt. They may vary a little bit, 10%, 5% variation. So we have to watch out for that as well. The resistors that you see here also change. They have a tolerance. Okay. So there are a lot of things which are causing deviation in the bias point, and we have to watch out for all of them. And in that context, we had seen that if you don't want your bias point to be very sensitive to the supply voltage here, small changes in supply voltage should not result in disproportionately large changes in current, then we need to keep a substantial amount of RB here. But then the drawback was that if you keep RB here and you attach a signal here, the signal gets dropped across RB, and we don't want that. Because for amplification, remember what we want? We want this entire signal to appear across the base emitter junction here. The amplifiers work. Why? Because the signal modifies the base emitter voltage, which modifies the collector current, and then modification in collector current results in modification of this voltage here. So your whole goal is that the entire signal that you see here should appear across the base emitter junction. And with that in mind, we separated the path of the signal and we attached it here. And so as not to upset the bias point, the capacitor has to be attached, otherwise you won't get proper biasing here. So we arrived at this particular circuit here. There are many other, based on the same principle, there could be many other variations. Maybe we could have done that. We could have kept the circuit as it is, and instead of attaching it from here, maybe just bypassed it here. Okay, then the signal here will go and through the capacitor and will appear across the base emitter junction. We could have done that as well. The other possibility is, what about here? By the way, this circuit is just similar with this. The whole idea is why keep two supplies here, VCC and VBB. Why not just use one supply and bias it? So this circuit is practically the same as this, okay? A little bit more efficient in terms of usage of power supply here. So this is same as this. What about this one here? What about this solution? Remember what our goal is? Our goal is to bias the transistor as well as apply the signal such that the entire signal appears across the base emitter junction. Would this work? In what sense will it not work? Let's look at the biasing. If I look at the biasing, I would put this, let's say the signal is not there, so this is ground. And I have a, you'll have to use a negative voltage here. So you have a negative voltage, RE, and if you write a KVL in this particular loop, you'll find biasing is fine. You can use a suitable value of VEE and a resistor R, and you can bias it at whatever current, whatever voltage you want here. Okay, so biasing is not a problem. Where is the issue? The signal that you see here, where will it drop? Look at the path of the signal. The signal, you start from here, go here, and then come back here. Under small signal condition, this will be ground here. So you can see here, the signal will drop partly here and partly across RE as well. Same thing that was happening here. The signal was dropping across RB and was dropping across the base emitter junction. Same thing is happening over here as well. The signal is dropping across base emitter, but will drop across RE as well. Now, how do we get rid of that? Well, maybe we could do this. We could attach a capacitor here at this particular node. So now, as far as DC is concerned, remove the capacitor, put it to short. You'll find that is biased properly, no issues. And as far as small signal AC is concerned, well, this signal is going to go here, come here, and this part, remember, would be shorted to the ground under AC operation here. If the signal frequency is such that the impedance of the capacitor is very small, then this point would be like an AC ground. And therefore, the entire signal that you see here would appear across the base emitter junction. That's what you want. Okay, so that could be another solution. It's not that this is the only solution which is available in terms of biasing as well as applying the signal. This could be an alternative solution. And maybe in the homework assignment, what we would try and do is compare this solution versus this solution here. What are the implications of these two solutions here? Okay. And so one obvious, in fact, compare this one with this particular one. One obvious drawback of this particular one is that you have to use an additional supply. You use an additional supply which is negative. That's an obvious drawback, while this one does not, it just uses one positive supply here. Now, when we evaluate two amplifier configurations, there are a series of parameters that we need to use. And we need to evaluate them not in terms of just in terms of one or more component, but also in terms of how stable is the bias point, what are the voltage gains, input resistance, output resistance, frequency response. All those things we'll have to evaluate before commenting as to which circuit is better. Is this better or this better? the comparison is not so straightforward. It's not just in terms of one extra battery here. If there are substantial advantages that this offers compared to this, then it may not be too much of a drawback here. Now, while we'll come back to biasing later on also, but while talking about biasing, what I want to point out is there are two distinct ways of making circuits. One of them is what we call as a discrete circuit. Discrete circuit which is made on a printed circuit board, PCB, using discrete transistors. You see all these transistors and resistors and capacitors and all that may be there. And by discrete component, we mean a component which has been prefabricated and is packaged and is available as a separate entity. So you take that transistor, you take that resistor, all of them have been prefabricated and they're available as discrete components. You take them and you connect them up on an insulating substrate, a printed circuit board, and you make a circuit. The other one is where you make the circuit not using these discrete transistors and resistors and all that. You make the entire circuit on silicon itself. So you make the transistor on silicon itself, you make the resistors on silicon itself, you make the capacitors also on silicon itself. So the entire circuit is made on that piece of silicon, and this is what we call as an integrated circuit. In some sense, both of them are integrated circuits. You are integrating components here and you are integrating components here as well. But we reserve the name integrated circuit for this one, by which we mean that all the components are fabricated on silicon or other substrates as well, but the dominant substrate is silicon. So you fabricate the components on silicon and you connect them up on silicon itself. Note the distinction. Here the components are available separately. You just go pick and you place them on your PCB and then you interconnect them. Now, there are two distinctions between these two classes of circuits. One of them is, when I look at a discrete circuit, resistors and capacitors are very cheap. In the lab, when you go and use, resistors, you can buy resistors and capacitors, and, the person would not count maybe the resistors and capacitors and would actually weigh it. You want half a kg of resistors or half a kg of capacitors. Okay, they're very cheap. So you may weigh them and then use them. What is expensive is the transistors. If I look at resistors, capacitors, and transistors, the most expensive component would be the transistor. On the other hand, if I go here, if I go on an integrated circuit, the transistor is the cheapest element. The transistor is the cheapest element. The resistors are more expensive, and the capacitors are even more expensive. Now, what do I mean by expense? When you make it on a piece of silicon, the expense comes from process complexity and all that. But a simple measure of how expensive a component is how much silicon area it occupies. So what you find is that the transistor usually occupies the least area, least silicon area. Okay, semiconductor or least area. The resistors, especially when you go to large value resistors, become difficult to make. And they're usually expensive. They occupy more area. And capacitors are very difficult to make, especially if the capacitors are of large value. See, here you can go into the lab and pick a capacitor of 1 microfarad, 10 microfarad. They're easily available. Just go and pick a 10 microfarad capacitor and you can put it in your circuit. Well, you can't make a 10 microfarad capacitor on silicon. It would occupy such a large area that is simply not feasible. So if you're looking for a 10 microfarad capacitor in your circuit, well, you can't make it on silicon. You can't make even nanofarad capacitors. Even nanofarad capacitors will take up, if you want 2-3 nanofarads, that also becomes difficult. Capacitors which are feasible are in picofarads. 10 picofarad, 20 picofarad maybe. So those kinds of capacitors, 1 picofarad. So if you want capacitors of that magnitude, it's okay, you can use them. But any larger values, nanofarads and microfarads, are out of question. So you can see here that if I'm designing my circuit, then my philosophy would be different. In the sense that if I'm designing this particular circuit and the most expensive component is a transistor, most expensive component is a transistor, then what I would do is I'll use lot of resistors, lot of capacitors, the cheap components that are available, and use as few transistors as possible. On the other hand, if I'm making a circuit on the silicon itself, I'm going to use lots of transistors, as few resistors as possible, and if possible, no capacitor. If possible, no capacitor. Okay, so that's what I would try to do it. So you would obviously then see that the kind of circuits that I use when I think of implementation on a PCB would be different kind of circuit as compared to circuits that are suitable for implementation on silicon. So right now, when I'm talking about these circuits here, when I showed you a circuit of this kind, or a circuit of this kind and this kind, all of them you would see require capacitors. It requires a capacitor here, capacitor here, capacitor here. And what value of capacitor do they want? Do we require? Well, if you look at this one, look at this particular capacitor. We want this capacitor to be acting as a short at, let's say you're making an audio amplifier. Audio amplifiers, which means the frequencies can be as low as 100 hertz or even lower. So if you want your capacitor to act as a very low impedance at 100 hertz, and you know that the resistors in series, this resistor or resistor, especially this resistor here, a small signal resistance here, is in kilo ohm, then you would see that the capacitor that you require is in microfarads. So this solution, which is okay if you want to go into the lab and make it on a breadboard or a PCB, is fine. But if you want to implement this on a piece of silicon, you can't do that. You could implement all this, maybe, all this part here, but the capacitor will have to be an external capacitor. You can't build the capacitor inside the silicon. Microfarad capacitors can't be built. Similarly, if you look at this particular solution here, this also uses a bypass capacitor here, so that my signal source does not see RE. This capacitor would also be in microfarads, tens or hundreds of microfarads. So again, it's not suitable. It's not suitable for, if you're thinking that, okay, I can have one capacitor outside the chip. Most of it is inside the chip, but remember, most amplifiers would be multi-stage. Multi-stage means one stage like this, the output of this stage will be connected to the input of the second stage. So how would you connect? Well, you would require a capacitor here also to couple it to the next stage here. Right? So you can't just, you're not just building a one simple amplifier, one simple stage. You're building a multi-stage amplifier. So again, these kinds of things are not suitable. Not suitable for implementation on a piece of silicon. So we'll see later on that there are alternative ways of biasing which do not require a capacitor, which don't require a capacitor at all. So if you want as an interesting problem, we started off with this particular circuit and we said it doesn't work very well because the signal sees an RB. Now, if you can come up with a solution where you bias the transistor in forward active mode and you can separate the signal also, in the sense the signal sees only the base emitter voltage here, if you can separate them out and without the use of capacitors. No capacitors will be allowed. So can you achieve what this circuit is doing without the use of capacitors? Okay? Then that particular implementation, that particular design would be suitable to be put on silicon. Okay? So think of that. We'll come back later on in the course here. All right. So let's come back to our basic amplifier, common emitter amplifier here. And so we've seen a little bit about this amplifier, but let's go into more details here. So we would like to calculate the voltage gains. Two voltage gains, when normally there would be a load, so we call it AV. And AV0 is what we call as the open circuit voltage gain when RL is infinity. So these things have to be calculated. Rn and R0 have to be calculated. Rn means the input resistance looking from here, and R0 is the resistance looking from here. Okay, note that R0 excludes RL, is the resistance looking from this side here. So we need to calculate these two. We need to find out how large can V0 be, maximum output voltage swing. We need to look at the lower cutoff frequencies and upper cutoff frequencies. I've mentioned earlier, we need to look at the stability of the whole amplifier against all kinds of variations. Here I've mentioned the stability against variations in beta. Beta is one of the dominant parameter which varies a lot. Okay, so we need to look at all of them. So let's start and see one by one. Okay, so what I'm going to do is next mid-frequency analysis, which means whenever we talk about this gain, input resistance, F0, all of that, we talk about these quantities in the mid-frequency range. Okay, and when we talk about frequency response, then we say, well, we calculate FL and FH, and we say between these two quantities, FL and FH, these things are valid. All right, so we said that we would, all these quantities, gain, input resistance, and output resistance are small signal quantities. We can transform them into a small signal equivalent circuit. And since we are talking about mid frequency, the capacitors have been shorted here, capacitors have been shorted here. So you end up getting this equivalent circuit that you see here, RB, RPi, GM, R0, RC, and all of that here. And it's a straightforward circuit. I'll not go into it. Very quickly, you can calculate a voltage gain is minus GM, RC parallel RL. If you don't have load, if the load is RL is infinity, then you get open circuit voltage gain minus GM RC. Input resistance looking from here, from this side, you can see here, it is RB in parallel with RPi. So that's there. And output resistance looking from here. When we calculate output resistance, what we do is we short the source. So we short the source here. When the source is shorted, there is no VBE, and therefore this current source is open circuit. And when you look from here, all that you see is R0 in parallel with RC. So that's the output resistance. So very easy to calculate open circuit voltage gain, Rn, R0 gain. All right. What is the significance of beta for the amplifier? Should beta be high, medium, low? What do you want for the beta? How important is beta for amplification? Well, let's look at the gain. Since this is a voltage amplifier, voltage gain is obviously important. So let's look at gain. AV0 is minus GMRC, open circuit voltage gain. GM is IC by VT, ICQ by VT. So let's put that. Bias point are always denoted by capital letters, capital subscripts, and most of the time we'll add Q here, quiescent point, the bias point or quiescent point, okay, ICQ. So ICQ RC by VT. All right, fine. There's no beta anywhere so far. Is voltage gain independent of beta? Okay, all right. So I guess you would say, well, ICQ depends on beta. All right. So ICQ, everybody can see, ICQ is beta multiplied by IB, and IB is VBB minus VBE divided by RB. Fine. Okay. So let's put ICQ here. So let's put the value of ICQ over here. So AV0 is minus beta, VBB minus VB by VT by RC by RB. So is beta very important for gain? Is beta very important or not? Obviously. The answer is obvious, okay? Now, I mean, if I'm asking that question, most likely it's not so obvious, okay? All right, so let's see. So we all see here, AV0 is minus beta, VBB minus VB by VT, RC by RB. So, I guess by looking at this expression, we can say, would you all agree? Two amplifiers of the same design, the one which has a higher value of beta will provide a higher value of open circuit voltage gain. Same design means same VBB, same RC, same RB. If everything else is the same, then a design, a design which is done with a transistor of higher beta will provide a higher value of open circuit voltage gain. All right, okay. Let's redo the derivation. AV0 is minus GMRC. AV0 is again minus ICQ RC by VT. ICQ RC is the drop here. Is a drop across this particular resistor here. So I can write it as VCC minus VCQ by VT. Okay. AV0 is minus VCC minus VCQ by VT. Two amplifiers with BJT bias at the same collector emitter voltage will have the same open circuit voltage gain irrespective of the value of beta. All right, let me put both these statements here. I can write AV0 like this. I can write AV0 like this here. Two amplifiers with BJT bias at the same collector emitter voltage will have the same open circuit voltage gain irrespective of the value of beta. Is beta important or not? Huh? I mean, if you're saying, if I give you a value of, let's say one transistor has a value of 100 beta and another one of them has a value of 200. Why do I have to design them in the same manner? For one which is 100, maybe I can use RC by RB, whatever it is, as twice as compared to a amplifier for which beta is 100. Or as compared to amplifier with a beta of 200. So which is the correct statement? Is beta important for my amplification or not? So we say that, you remember we are saying that all amplifiers' properties depend on the biasing point. Now I'm saying two amplifiers, if I bias them at the same collector emitter voltage, will have the same gain, open circuit gain, doesn't matter what beta is. Obviously, if I take a transistor and bias it at different places, it will have different gain. You know, if you bias it at different ICQs, different VCQ, obviously it will have a different gain. So if I'm saying two amplifiers biased at the same bias point, then the gain is independent of beta. So I'm asking you, would you say that the gain is independent of beta, or does it depend on beta? Is beta very important for you, or is beta not important? Both statements are true, right? Depending on how you write it, both are true. VCEQ is? Yeah, VCEQ depends on how I design it. I mean, VCEQ is under, I have a choice regarding VCEQ. Let me ask the question, what is the highest gain that you think you can get from your amplifier? Highest possible gain that you can get from this amplifier? Let's look at this expression, will tell you. Highest gain? What will you do to VCEQ? If you look at this expression, what will you do to VCEQ? You'll make it as low as possible, but how low can I make? Well, if I make it very low, it will go into saturation region. And we said 0.2 is our limit. So maybe you can make it 0.2 or 0.3, let's say, stay away. So if you make it 0.3, then the maximum gain that you can get from your circuit, can I write this? Maximum possible gain that I can get from the circuit is VCC by VT. Because if VCC is large, 5 volt, 0.2 or 0.3 doesn't really matter. So the maximum possible voltage gain that you can get from your circuit depends on VCC by VT. Where is beta here? Does beta play any role here in terms of maximum gain that I can get? Whether I have a transistor with a beta of 100 or 200, the maximum gain that I can get from an amplifier like this is eventually limited by what? By the supply voltage here, VCC. Not by beta. Not by beta, it depends on temperature. That's why if you see the upper limit of gain, at least in a circuit like this, if you make a different amplifier circuit, you may have different issues, but at least in the basic common emitter amplifier circuit like this, the highest gain that you can get has no dependence on beta, just depends on the supply voltage and the thermal voltage here. And that's why what you find is it becomes so challenging to design high gain amplifiers for low voltage. If I want to run my amplifier on 1.5 volt, if I want to run it on 1.5 volt, if I put 1.5 volt here and thermal voltage as 26 millivolt, I find that the gain is less than 58. I can't build anything, no matter what you do, RC, RB, beta of 500 or 1000 or 100, no matter what you do, you can never get gain which is more than 58 at room temperature. On the other hand, if you calculate the gain at, if it's hot summer and the temperature outside is 50, then the temperature of the junction may be 75. If you calculate, you'll get even lower gain. So it's a real challenge. How do we obtain large voltage gain at low supply voltage? Suppose somebody wants to run an amplifier at 1 volt. Why is all this low voltage important, especially with all the portable applications that we have? Lower power supply, basically, which means that, all the portable applications, and also lower power supply means lower power dissipation. Because if you're running your amplifier at 1 milliampere current and you run it at 5 volt, you're drawing 1 milliampere into 5 milliwatts of power. On the other hand, if you run it at 1 volt, you're drawing 1 milliwatt here. Okay? So we want to operate things at low voltage, but then look at the challenge here. The gain ability of a single stage amplifier to provide a gain becomes small. So obviously, in what you would do is you would take one stage and cascade it with the next stage here. One stage gives you a gain of 50, another stage gives you a gain of 50, 50 into 50, maybe you can get large gain here. So from a single stage, the amount of gain that you can get is in this circuit limited by VCC, not by the beta of the transistor. Beta doesn't come into picture here. Okay. All right. Let's continue with this. So look at, but beta is, does it mean that beta is not important? Does it mean that beta is not important? Should be greater than 1. Why? Why should it be greater than 1? So that's the question that I'm asking. Why is it we are so fixated on beta? Why are we saying beta has to be greater than 1? So what if beta is, did our transistor action, when I talked about transistor, when I said an element is a transistor, why is it a transistor? Power output, but we also said, remember, that my collector current is more sensitive to base emitter voltage and less sensitive to collector emitter voltage, transconductance. In that, view, when I talked about transconductance and all that, beta was nowhere in the picture. To take an element, for example, all of you are thinking of beta because you are applying the signal from the base here. I can apply the signal from the emitter. Emitter can be my input, and collector can be my output. So when you look at emitter as an input and collector as an output, is there a gain between emitter and collector? What is the relationship between emitter current and collector current? Less than 1. Gain is less than 1. So when I use my input as the emitter and output as the collector, I'm actually operating with the current gain between input and output, which is less than 1, and it works as an amplifier. Current gain, as you see here, is not essential to amplification. But that's what I'm raising. Is beta important? So let's look at that. Beta is very important. But let's see how. So AV0, because remember, when you're building voltage amplifiers, it's not just the voltage gain which is important for you. We also said what is important for you is input resistance and output resistance. A good voltage amplifier should have very high input resistance, should have very low output resistance. These are all important for you, not just the value of the voltage gain. Okay, so let's look at AV0 is ICQ RC by VT. Let's look at Rn. Rn, we had derived Rb parallel Rpi. In most of the designs, you'll find Rb is much larger than Rpi. So as a first order approximation, we'll write it as simply as Rpi, which is Vt by ICQ into beta. Okay. R0, our output resistance is Rc, parallel the output resistance of the transistor. In most cases, you'll find R0 is much larger than Rc. So as a first order approximation, we'll just write output resistance is simply equal to Rc. Now note, as I said, for an amplifier, you want high gain, but you also want high Rn, and you also want low value of R0. Now if you look at these three things here, can you see a trade-off? high value of gain, well, one way of getting high value of gain would be large value of ICQ. And large value of ICQ, what will it do? Will make your input resistance small. Or let's say you want a large value of gain, then you would require large value of RC. And large value of RC make output resistance large, which you don't want again. So you see a trade-off between gain, input resistance and output resistance, and it's very simple to look at these three quantities and see that this is true. AV0, magnitude of gain, multiplied by Rn divided by R0 will always be less than or equal to beta. Now can you see the importance of beta? What is important for us? High gain. What is also important for us? High input resistance. And what is also important for us? Low R0. But all this is eventually limited by beta. So it's not gain per se. It's not gain per se or is input resistance or output resistance. The overall performance of the amplifier, which involves everything, gain, input resistance and output resistance, is eventually limited by beta. So if you give me two transistors, one with a higher beta as compared to the other, I can give you an amplifier with better performance, either in terms of gain or in terms of input resistance or in terms of output resistance. Eventually, note that you can play around with AV0, Rn and R0, but the product divided by this will always be less than beta. So that's the importance of beta that is coming out. It's not simply the highest gain that we can get, AV0 we saw, is independent of beta. Okay, is all of them together here. So you can see here, these are fundamental trade-offs in a common emitter amplifier and in most of the amplifiers here. So if I keep R0 constant, if I don't change R0, then any increase in voltage gain will be accompanied by a decrease in Rn. You'll get a trade-off here. You can get high voltage gain but low input resistance. You can get high input resistance but low gain. There's a trade-off here. Or if you keep Rn constant, then again you see a trade-off. You can get higher voltage gain, but you'll have to increase the output resistance. Or if you don't want to touch the gain, you see a trade-off again here. A large input resistance is accompanied by large output resistance. Basically a plot of this relationship here. AV, Rn by R0 always has to be less than or equal to beta. And tells you the important trade-offs that are there in my transistor here. So the performance of a BJT voltage amplifier is ultimately limited by beta. How large a gain, how large an input resistance, or how small an output resistance you can get is eventually all limited by beta. That's the importance of beta. If I have a beta of 1, you're right, if I have a beta of 1, my ability to get, it's not that I can't get voltage gain. If I have a beta of 2, it's not that I can't get voltage gain. I'll be able to get voltage gain. You can take an amplifier and, in simulation is easy. Just put beta equal to 2, design it properly, you'll get voltage gain. You'll get also power gain. That's not a problem with the beta of 2. But it will not be a very good amplifier. Because when beta is 2, somewhere you are compromising. You may be able to get gain, but your Rn may be very low. Or your R0 may be very high. And so it's not a very good amplifier. But you'll be able to get AV0. Okay, but overall ability is limited by beta here. So let me give you one design example. So I took RB of 200K, RC of 2K, VCC of 5 volt, and beta is 100, and this is 10 microfarad here, and we get, for this bias, you can calculate it yourself. ICQ is around 2 milliamperes, VCQ is 0.7. We have really pushed it close to the saturation. Saturation would be around 0.2 or 0.3, so it's close to that. For that, we get voltage gain 165, input resistance 1.2K, output resistance is 1.92K. Note that output resistance is very close to RC, 2K here. It's practically equal to this one here. So, now, these are some typical conditions for a common emitter amplifier. And many times when people look at these numbers, they say, well, the characteristics of common emitter amplifier is that it can give you high voltage gain. Voltage gain is high. That it gives you medium input resistance. So the number, many books, many times when we are talking about it, a 1 kilo ohm, we call it medium. All right, it's like a medium value. Again, these are arbitrary. I mean, what is medium, what is low, and what is high? These are arbitrary. Okay, so but 1 kilo ohm is called medium. So we say input resistance is medium. Our 1 kilo ohm, around 1 kilo ohm, so output resistance is medium. So when you read books, you'll find that very often it is said that a common emitter amplifier can give you high gain, or a characteristics of common emitter amplifier are high gain, medium input resistance, and medium output resistance. Okay, let me give you another design. Note the difference. This one was biased at 2 milliamperes. We bias now at 52 microamperes. VCQ is 2.4. We get 100. Rin of 50, R0 50. Gain is high, fine. What would you call input resistance? Medium? 1K is medium. 50K? High. 50K output resistance? High. So would you agree with this? That common emitter amplifier gives you high voltage gain, medium input resistance, medium output resistance? Well, I just gave you another example. High and 3 highs, right? High, 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 right? Oh, everything is high. We got all high values. All right? All high values. You think I can get all low values? Can I get all low values? Low, low, low. You think I can get that? All right. So what I'm trying to point out is, this is many times when you read books, you find discussion like this. Okay. This is from Cedra and Smith. So this, for example, it says input resistance is moderate to low in the kilo ohm range for a common emitter amplifier. Input resistance is moderate to low, typically in kilo ohm range. Well, there's no reason for it to be low. As I said, if you want high, you can make high input resistance. 50K is possible. I can also design it for 100K. What it says also, to obtain a high input resistance, the bias current can be lowered, but this lowers the gain. So what it's talking about is as if I can get high gain only by sacrificing, or I can get higher input resistance by sacrificing gain. That's what it's talking about. Point number 1, that if you want high input resistance, then you get lower gain. But look at this expression. Can I get high input resistance without sacrificing gain? I can leave the gain untouched. I can leave the gain untouched. I can get high value of input resistance, but I'll sacrifice R0. So that's an alternative point which is not talked about. Or you say the output resistance is moderate to high. Reducing RC to lower value is not a viable proposition because the voltage gain is also reduced. So it's saying if you want lower R0, you have to sacrifice gain. Well, I can leave the R0, I can leave the gain unchanged, I can reduce R0, and I can reduce Rn. All right. So these pictures that you see here are partial, they're not complete. They're not giving the complete picture. The complete picture of a common emitter amplifier is not in terms of high, low, high, high, medium, high, and all of those things. The complete picture of an amplifier is this relationship. This very simple relationship. AV0, Rn by R0 has to be less than or equal to beta. That's the picture of a common emitter amplifier. You can get a value of gain which is high, and you can get this also high, but then obviously R0 would be then determined by this particular relationship. Okay, so this actually summarizes what a common emitter amplifier is in terms of its capability. If you have a high value of beta, you can build a better amplifier. If you have a low value of beta, well, you'll have to struggle with, you'll have to compromise somewhere. Okay? Yes. Yes, we said a good voltage amplifier has a low output resistance, high input resistance and a high gain. Now, is high value of R0 a problem? See, problem or not a problem, it all depends on the context. All right. I may have a high value of R0, very high value of R0, let's say. And the next stage after that is, let's say, a MOS amplifier, MOSFET. Now, when this signal goes into the gate of the MOSFET, when you look into the gate of the MOSFET, you see very high impedance. So it doesn't really matter. Maybe. Okay, so high or low, what is very high, what is moderate, all those depends on the context. Okay, so, so that's what I want to get away with. Do you always want a output resistance as low as possible? The answer is no. Do you always want input resistance as high as possible? The answer is no. So how much input resistance, how much output resistance do you really want? Well, it depends on where you're going to use it. Okay, so it all depends on that.